and welcome to lesson 1.01, Limits Graphically and Numerically. In this lesson, you will see how to estimate a limit using a numerical or graphical approach. You will also learn different ways that a limit can fail to exist. So as an introduction, consider the following function. It's a rational function. What are some other things that you might notice about this function? Well, if we try to use the value x is equal to 1, we get 0 in the denominator. So one of the tools that we can use outside of our algebraic tools is the idea of considering what does the value of f of x approach as x gets really close to 1. So using a table of values and coming in from both the left and the right side and creating a smaller and smaller neighborhood around 1, you can see that the value of f of x does seem to be approaching a single value of 3. Okay. And this would be read as the limit of f of x as x approaches 1 is 3. Okay. Now, let's look at this function from a different perspective. If we were to graph the previous function, it shows that the value of the function actually doesn't exist. And you might know this from Algebra 1. This is what's called a hole. Okay. But if f of x became arbitrarily close to a single, if f of x becomes arbitrarily close to a single number L as x approaches C from either side, then the limit of f of x as x approaches C is L. And this limit is written as the limit as x approaches C of f of x is equal to L. And as it applies to this function, we would say that the limit as x approaches 1 of f of x is 3, even though the value of the function doesn't exist. So as an example, let's first evaluate the following function at several x values near 0 and use the result to estimate the limit. Then we'll use a graphing utility to graph the function and verify our answers to A. So using a graphing utility, we can see that as we get really close to 0, at 0 there is an error, but it does seem to be approaching a value of 2. Now I've left some instructions in the bottom of the slide deck if you need help creating these tables. The left table is created with a TI calculator and the right table is created with Desmos. Okay. Now graphing the function, we can see that from both the left and the right side, the function does appear to be approaching 2, but the value at 0 doesn't exist. Okay, another example, and in this case we're going to show that the limit as x approaches 0 of the absolute value of x divided by x does not exist. So just as a reminder, the definition of absolute value. We say that the absolute value of x is equal to x when x is greater than or equal to 0, and negative x when x is less than 0. Thus, the function absolute value of x divided by x is always going to be either 1 or negative 1, depending on what the value of x is. Graphically, we can see that from the left and the right, our function approaches two different values, 1 and negative 1. So no matter how close x gets to 0, there will always be both a positive and negative x values that yield either 1 or negative 1. So because the function approaches a different number from the right side of 0 than it approaches from the left side, we say the limit does not exist. A limit that does not exist is sometimes referred to as non-existent, for instance, on the AP exam. Can you think of any other possible scenarios where a limit might not exist under the previous definition of a non-existent limit? So as one example, sine of 1 over x, this yields a function that is called an oscillating function. It bounces back and forth between negative 1 and 1 as x approaches 0. And that's infinite times. It bounces back and forth. There's not a finite number of times that it bounces between negative 1 and 1. And so because no matter how close we get to 0, there's never a guarantee as to whether the function will be 1 or negative 1 or somewhere in between, we say that the limit does not exist. And another example, this is an example of where we would have an asymptote. A limit does not exist at an asymptote because from the left and the right, as x approaches 0, the function approaches either positive or negative infinity. In fact, even if a function approaches the same infinity, for instance, the limit as x approaches 0 of 1 over x squared, both sides of the function approach positive infinity. But because infinity is not an attainable value, we still say that the limit does not exist, or that it is non-existent. So in summary, a limit is a value that can be defined as the function value, L, that is approached when a value of x gets infinitely close to a number c. And some common types of behavior associated with non-existence of a limit are listed below. See you next time.